So first of all, thank you for the invitation. It gives me something to do and at least come here and visit the locale of links, because otherwise I was not moving from my area of Paris. And also I think it's a day that reminds me that I could be in Waterloo because the weather is like that. Except that Waterloo might be a little bit colder, but it's I think -5 this morning it was here. So that's a typical end of winter day in Waterloo. That means we are getting ready for spring. Okay. So anyway, so today I'm going to talk to you about real-time bidding in first and second price auctions with temporal and targeting constraints. This has become a very important problem, especially because today the notion, and I will describe what the bidding process and what we are bidding for, is beginning to change. That originally the second price auction was an important concept, but I see in the last 3 months a number of papers talking now about first price auctions. Now it turns out, and I will tell you this, that this problem was first proposed to us, actually to Peter Marbach and I, over drinks in Toronto by the CEO of a company called Addictive Mobility, to whom I really must thank, because they gave us the problem formulation. They also gave us money because he was a very far-sighted CEO. He says, I'll give you money because I believe math can be applied to this problem. And if it can be applied and you can help us, that'll be great. If you cannot, that's fine. I've given money for a good cause. So that was great. You know, he gave us $275,000, which is pretty good for a CEO of a small company. And, you know, he was willing to pay that because we could take $275,000 and, you know, we could get it tripled through the government of Canada. So really it became like $800,000 grant. But, you know, he gave it from his own pocket, not even from the company. So he was a very remarkable guy. So, and so we started thinking about the problem. And the first thing we realized is they gave us access to their data. And they said, we are doing this. What can you do better? So anyway, so this is joint work, therefore, with my PhD student, Ryan Kinnear, who I think some people here at Links might know, because last time I came on sabbatical, he came and occupied a desk here, a very bright guy, and Peter Marbach at the University of Toronto. Okay, so, what's happening? I have to go. Yeah, I have to. Okay. So the question that I'm going to talk to you about is when you open a computer or a web page, an ad gets placed. And an ad gets placed because there are advertisers who want to place there. And the publishers are the guys who own the web page and that space on the web page. Question is, how does this happen? Right? On what basis? And so I will try to give you in this talk, what are ad auctions? What are they and how are they run in practice? The second thing I want to ask is, when we want to mathematically formulate this problem.
Yeah. Ravi?
Yeah?
We are not seeing the slides moving. We are just seeing the first slide.
Oh.
Your homepage.
So I don't know what's happening.
You need to click on the resume share.
Yeah, maybe resume share. Sorry about it. I'm clicking on it. Let me go back. Thanks for telling me. I don't know what. Okay. No, I'm just going back.
It's saying something below in orange. Sharing is paused.
Sharing is paused. Bring your shared window to the front.
My suggestion: stop sharing. Yeah. Stop share.
And restart it.
Yes, and then we start the whole desktop.
Yeah.
Instead of just.
Let's see what's happening. So cannot escape.
Step 1, stop share.
Okay, stop share. Okay.
Share again, share screen. Yes. At desktop, just have a full desktop, that should take care of it.
Yeah.
Yeah, sure. Okay, the bridge, can you see the?
Yeah, we see the slide.
Okay.
Okay, so I don't know how to go back on this. How do we
Just
go
go to your
back?
PDF.
Click on the slide.
Don't post share, just
Click on the slide.
Okay.
Yeah.
Yeah. Okay. So I want to talk about ad auctions, what they are and how they are run, and the notion of what is an information state. So what information do you need to make a bid? And the first thing I will say is that what made us think of what we need to bid is we created a generative model. So this model is just a model which suggests what to measure. And then we realize that there are important things, and I'll talk about it, and I'll tell you what is different in this work is very general, about targeting sets and campaigns, what they are. And then I will get into the sort of the details of the formulations and the solutions. So this talk will really, I'm going to focus on what are called bidding strategies. How much should we bid every time we want to get do some real-time bidding? So what do we need to formulate the problem, the market dynamics, and some things related to convexity issues, and something we realized from the analysis, something called pseudo-bids and bids. What are they related? And finally, I'll talk about how does one apply it in real time. So first, let me talk about what is a real-time bidding process. So a user, right? A user goes to a website or they open an app. So we were driven by the problem of addictive mobility, who were providing what we call ad placement on mobiles applications that you open. So for example, you know, they know a lot of South Asians in Toronto like to watch cricket. So there's an app called Cricinfo, which gives you all the cricket scores. And they also know South Asians who congregate in a western part of Toronto called Mississauga. In fact, that city of 800,000 has a majority population of Indians and Pakistanis. So they realized by just surveys and all that, that Indians and Pakistanis like to buy Honda Accord, safe car, right? They don't like to buy any fancy BMW. So they realized that anyone who opens a Cricinfo web app should be shown Honda ads because they're likely to click on them and buy. So these are targeted ads, right? So you can target age, sex, ethnicity, location, you know, all these various aspects, preferences, and so on. And these are what are called targeting criteria. So the moment a user gets on and they open a website, a lot of these things are known about them. And so what says the website has this place to paste an ad. It sends a message to the ad exchange, and the ad exchange then asks bidders, you bid to place your ad on that exchange. And a bidding process, what is called closed envelope bidding process takes place, in which everybody submits their bids and the bidder with the highest bid wins. And depending on the auction, if it's a first price auction, they will pay the highest price bid, which is 0.00042. Or if it's a second price auction, then they will pay the second highest price bid here, which is 0.00039, right? So this is how these auctions are run. Now, there was a philosophy that second price auctions are good because they are preference revealing, they have all these nice properties and so on. But increasingly, what people like Google and all of the Google Exchange, realizes that in fact, it's much harder to run second price auctions, and there is a move towards first price auctions. And that's why, as I've said, in the last 2-3 months, I've seen papers come out where people talk about first price auctions. However, I must say I must say, as somebody who's worked on this problem concretely, none of the papers that are being written have any sense in terms of marketing. You see, because you cannot work with utility functions and all that. No, this is not given to you, right? So people take their utility functions, they optimize it and do this, and they write, machine learning algorithms and so on. It just makes no sense for this problem. And that's one of the things we realized when working with addictive mobility. All this type of fancy things we do is really not relevant to the problem. It's one thing to write a paper, it's another thing to find an algorithm to implement. Okay. So what happens is that rather than this scenario where each sort of bidder to place the bid plays, what the industry has gone to are something called service side platforms and demand side platforms. So what it says is that a DSP is an aggregator. So addictive mobility, for example, ran campaigns for Honda, Coca-Cola, various sort of say Domino's Pizza, a number of companies, right? And each of these ad campaigns, as they were called, would have different requirements because they target different audiences. Pizzas would target young people, Coke would target young people, and so on and so forth. So DSPs act as aggregators who bid on behalf of the advertisers. So when a user goes on, sorry, I keep on thinking. When a user connects to a publisher, so this is called the supply side platform, right? So it's a publisher who owns a website or an ad and so on. The the ad exchange immediately gets into action, and the various DSPs which run various campaigns see what is the profile of the user and start bidding. Okay, and not all their profiles could match. For example, some parts of the profile could match. So for example, they could be targeting people like me over 65, okay, and so on. So so there is and this whole process takes about 0.05 seconds, 50 milliseconds, but typically it's 100 milliseconds is the time in which you log on to a website or open an app. It sends a message to the ad exchange. The ad exchange gets a bid from the DSPs on whose ad to place. So this either first price or second price auction is done. The winner is decided, the ad is placed, and then it is shown to you. And this is 0.05 seconds. So 50 milliseconds is actually it's about 100 milliseconds, which is the time given to you to process this application. So any mathematical algorithm that you can devise must operate at this time scale. Okay, and that I'll show you later on in the talk forces you to do something very different. So the first question is, what do we measure to make our bids? And so I'm going to begin with a simple model that tries to capture something, but it tells us what to measure, most importantly. This is what I call the information state of the problem. So suppose at time t, there are nt bidders, and a bidder behavior is described, and they are by bids over m classes of items. Okay, and we'll see what these classes of items are. And the bids are B, and Rij is just the probability that the bidder I will bid for item J, and the bid is actually Bij. Okay, and the winner of this auction is always the bidder who bids the highest price, but the payment depends on whether it's a first price auction or a second price auction. So a bidder who's bidding in a first price auction will pay what they bid if they win, and a bidder in a second price auction will win if they're the highest bidder but pay the second highest bid. Okay. So the question is two things. Is there's something very interesting about the problem. You get information of the market and about the prices only if you win. Otherwise, you don't see the prices. Right? So only if you bid and win do you know what the price is. And two, in a first price auction, you see, the winner, of course, you bid very high, it's very likely you'll win. But what happens is the following. The way the contract is set up with a DSP is, for example, let's say Coke will come to Addictive Mobility and say, run a campaign for me from 15th of January to the 8th of, let's say 15th of February, 1 month, targeting this group of people in this part of Toronto, because there are maybe, let's say something going on over there. And I'm going to pay you, let's say $10,000 for running this campaign for 1 month, but you must guarantee me that you will at least show my ad 100,000 times. Okay, this is how contracts are written in this industry. So if I'm a DSP and I've taken on a contract, I know I have to show 100,000. I've been paid 10,000. So it is in my interest to bid and win at the lowest possible price. Because the price I'm paying and the amount I receive the contract, the difference is my profit. Right? So many formulations that you see in papers, academic papers, deal with individual utilities and deal with budget constraints and so on and so forth. This is not the way the problem is formulated or required. It is formulated in terms of the number of impressions that the company requires and the duration for which this campaign has to be run. Okay. Okay. So now,
Ravi?
Yes.
If you are paid as a DSP only based on the number of times that it is shown.
No, not number of times. You have to guarantee that so many things will be shown in the campaign. So, for example, suppose I'm a DSP.
Right. Sorry, that's exactly my point. Sorry, I misworded. So the number of times that is shown, you may want to bid for things that are very low price, but even if you want, it will bring almost anything for the client. So it should be other criteria, right, for validating the campaign.
No, you see, but there's the other thing, right? Sure, for example, suppose the price today and tomorrow, because it's called very low, okay, I can bid and get a lot of impressions. But the problem is that I have to balance my campaign over the duration. And so often there are constraints that saying, show at least 1,000 ads per day, right? So you have additional constraints.
Yeah, I'm sorry, I misformulated my question. I understand that I'm not formulating it correctly. What I'm saying is that if the only criteria to evaluate if I am doing a good job is how many times my client is shown in the space, in the ad space, I may select spaces that are cheap, which are not very relevant to my client. But
I see your question. So the question is the following. You see, all of this business is based upon reputation, because what the advertiser will actually see as feedback are click-throughs. Okay, so how many people click on their ads and what is the profile of that? So that information is available to them. Okay, so in some sense, there is this feedback mechanism to assure that DSPs bid for them in the right space and are doing the right thing. Does that answer your question?
Yes.
Okay. Yeah. So that for sure. And this is an industry based upon reputation. Is the DSP providing the service that the advertiser is charging? Of course, I can show you can put all those constraints into the formulation, but I'm getting to the basic problem of formulating this problem right now. Okay. So the first thing we know is that the probability, so now suppose I'm an exogenous bidder and WJT is the maximum of the other prices of the other bidders in the system for item J. Then clearly I will win if X is greater than WJ because WJ is the second highest price. So in some sense, I need to compute this distribution function, which is the probability of winning. Okay. And so, and then you can write the win probability in terms of the bids through this very simple expression. Okay. And I put T over here because this is the bid at time T. Okay. So now the question is, this is the probability of bidding given that there are these people, but how does it, you want to go a little bit more. So now let's take, it is a generative model. I'm not saying it's the truth, but this is how we believe things happen. So users arrive, and let's assume they arrive as Poisson. Then the number of users, and they have to interact for this, let's say 100 milliseconds, that's your time of placing your bids and coming and receiving it and getting out. So you have these number of users, and so the stationary distribution corresponds to the stationary distribution of an MG infinity system. And of course, that we know is a Poisson distribution. And so from that, immediately plugging in, we can actually compute the average, right? We can compute the average win probability as this quantity. And we'll call this average bid quantity something called a supply curve. And I'll come back to this very shortly. So now we have to begin to talk about how these impressions arrive. So if you look, really go to an ad exchange and you look at how these things come about. So at this time, the ticker tape will show I have, I have 500 impressions available for this profiles. Okay. So the publisher will say, I have 500 impressions, and who is going to bid for this space? It's not one impression at a time, but 500. Next instant, it could be 625. Next instant could be 728, and so on. So I have 500 impressions, and I can place them on these following web pages, or I can place them on these following apps. Who is going to bid? So I, as a DSP, I can bid for the 500 items, or I can bid for 300 items, or whatever, so on and so on. I'm not bidding of an item at a time. Right? And so and then based upon this auction mechanism, I'm going to win or lose, and so on and so forth. So that's why these auctions are far more complex than bidding on single items. Right? It's like actually playing on the stock market. You know, when you look at a stock ticker tape, when it says the stock price of Alstom is 1.51 euros, you also get a quantity associated. That's what is available at that price. So a broker will then go and place a bid for 200 items at 1.51 and so on and so forth. So they buy these shares, right? So it's exactly like that. Now, it turns out, so if the arrival rate is lambda, it's a function of time, then the average, in some sense, the supply that arrives at time in an interval of 0 to t is lambda of t times this W. So you think of W as a distribution function which gives you the number of items, right, that arrive at every time, the average number. And of course, the question is, how do you measure this? And like I said, measuring W of X is an important problem. It's an important problem because you only get information about the system or price when you win, because you know the second highest price paid. In a first price auction, you don't get that information either. You won. That's about it. So you know everybody else has bid below you. That's about it. You don't have any other information. And so it turns out that this estimation problem is a very important problem, and I'll tell you how they do this. Okay, so this is an example. I don't know. I'm sorry about this curves, but I should have put them in separate pages. But the top, these curves show the arrivals of, so these show the arrivals of these impressions, as they're called. And from these impressions, you measure the supply curves, which says that if I bid 4, I will get 20K impressions. If I bid 10, I get 80K impressions. And as you see about these bidding curves, they don't have any nice properties of convexing. They are monotone increasing, and they're really distribution functions. So in a paper that in Sigmetrics last year, Peter Marbach and I wrote, we considered this problem over one period and not on this sort of this time horizon that I've talked to you about today. And this was actually, so this supply curve was actually a supply curve information that we got by looking at data when helping additive mobility. So this is actual data. This is how the estimations come about. And here, what this graph shows is really this part you measure, and what then those people try to do is they actually try to use these past measurements to predict the future. Okay, to get some finer estimates. Okay, so let's set some notation. So there are M item types. J belongs to 1 to M. There are N campaigns or contracts that are signed. And I'm just going to say, without loss of generality, the ith contract has a duration 0 to TI. Now you can ask me, why am I starting everything at 0? It really doesn't matter. They could be they could be staggered, but they have a starting time and a final time, which is the duration of the contract. And this is a deadline by which the contract must be fulfilled. Then we have a AI. This is the set of AI, which is the set of items J, which correspond to criteria associated with contract I. So contract I is, like I said, Coca-Cola advertising campaign, targeting, let's say, 16 to 24-year-olds in a certain part of Toronto and in a certain part of the year. And maybe they will differentiate based upon sex, whatever they want. Okay. So AI consists of all those things. So between 16 and 24, Toronto, this time of the year, and so on. CI is a constraint on the number of impressions required by a contract by time TI. Right? So at least so many impressions must be obtained, and then we order these times just to make the analysis less complicated in order of their deadlines. But this is also strictly not necessary if you realize what to do. So let me see, the first thing we need to do to be able to solve this problem is to do a decomposition of the target set. In other words, if these AI, so A1 is the targeting set or targeting criteria for the campaign 1, A2 is for campaign 2, and A3 campaign 3. So you see, this is a very general setting because there are intersections in the targeting set, right? And so to make the problem tractable, you have to find a decomposition which there is no overlap. And so you can find a collection Bj such that if I belongs to Bj, then J must belong to AI. So you have a decomposition of these sets, which you can do, and it's finite. Okay, so here is a decomposition of all those targeting sets. So for example, here B2 will only target, right? Campaign 3. I'm sorry, I just number it this way. Okay, so B2 only targets campaign 3, B1 targets only campaign 1, B3 targets only campaign 2, and these are common and so on, right? But there's granularity of separation going on. And so we think of the J as the campaigns, as this is the information we require about the supply curves of these various regions. Okay. And so once we have that, we're going to make an assumption. So every item of type J is associated with supply curve Wj, and it could be thought of as an unnormalized cumulative distribution function with respect to a bid argument x. So x is the bid, t is the time, and wjxt is on average how much you'll receive if you bid x. And so the assumption we make for supply curves, the functions are strictly monotone increasing. That means they have densities, right? If they're distributions, they have densities, positive and continuous. And suppose there's a soup, which is either infinity or some finite number. And we will see that the first price auction, in fact, to be able to solve it nicely needs further assumptions, and these assumptions are almost always met in practice, but it needs an additional assumption. So let fj of xt be the cost occurred at time t by bidding x for item j. Okay, so now I'm going to suppress the j because it's true for all j and all t. In a first price auction, you pay what you bid. Sorry. You pay what you bid, x, and the amount you have got on average is w of x, right? Because that's your supply curve. That's your supply. So xwx is the total cost for you for placing a bid x for item j, whose supply curve is wj. And in a second price auction, since your bid x you have won, all the other bids are between 0 and x, you don't know, so you just integrate this. And so the cost of the second price is just xwx. So it's just the Still-J's integration by parts of this. And so immediately you see that the cost that you will incur in the second price auction is lower than the cost you will incur in a first price auction as a bidder. Okay. Okay. So now we can begin to formulate the problem. So the goal is to find a bid path, so a bid for any time t, and an allocation path. And I'll tell you, because I can bid for more than one item and I win, I have to allocate those quantities that I win to all contracts for which they would be valid. And so you minimize them over all I. And gamma ij is the proportion that of j you allocate to contract I, and fj of xijt, this is the amount you will pay, the cost dt. So you want to minimize the total cost, and this is your constraint, which is the fact that the number allocated to I, integral from 0 to ti, because that's your duration, must be greater than ci. The other thing we know is this, since this allocation is just an allocation of all the items, so gamma ij, summation gamma ij must be less than 1 and it's greater than or equal to 0. So the first thing to think about is gamma ij could be thought of as the probability of allocating it. If you think of one item, it's a probability of allocating that item of type j to contract type. Okay, so you could think about it that way. Okay, so the first thing is we have this optimization problem, and what have we made assumptions about? Just w of x is continuous in x, monotone increasing, and the actual measured curve is a distribution, so it is just strictly right continuous and increasing like a distribution function. But in an earlier paper with P1 period, we show that when you have these jumps, what you do is you need to randomize, and the effect of randomization is smooth that curve. So that's why we assume it's a smooth curve. And so you want to optimize this function. And so the first thing is we define these quantities called lambda j of ST, which is the acquisition cost, which quantify instantaneously at time t the average cost of acquiring supply at rate S. Okay, so this is in some sense this quantity which is F composed with Wj inverse, and Wj inverse exists because we assumed it is monotone increase. Right? And so if you look at the second price auction and you write the cost, well, it turns out that the second price, if W just has this monotone increasing properties, this quantity lambda j turns out to be convex. So you get convexity for free in a second price auction. Now, in a first price auction, we'll see because the cost is x W of x, and there's no integration involved, you don't get convexity. And so you need something further to get convexity, and that is log concavity, but you need actually a weaker condition than log concavity. And this is what I call alpha concavity, which says that if you can define this function LA of x as either log x if alpha is equal to 1, or this quantity otherwise, and L2 is just this function 1 minus 1 by x, then we say a positive function W is strictly alpha concave if L alpha composed with W is concave. So it turns out, of course, that if a function, if alpha is equal to 1, it's log concave, and if alpha is equal to 0, it's just the identity function, and so the original function is concave. So it just generalizes concavity, and then you know that if alpha is less than beta, if it is if it is alpha concave, then it's also beta concave. These are properties that you can show. So for the first price auction, what we will assume is that the supply curve is strictly 2 concave and of this type. And if again one needs complex conjugate, this complex conjugate also has nice properties of convexity. Okay. So that's what is this property. Okay. So now, given this, we reformulate that original problem in terms of the original costs, in terms of these. So if I recall, you have an original problem in terms of F, and then we define these acquisition costs. So we can reformulate this in terms of acquisition costs. And so it becomes a problem of minimization over all items J, as opposed to you've gotten rid of the i's. And why? Because it turns out that this convexity really shows you that the bids, and this is a very, very important thing that you get, is that the bid for contract I bidding on item J only depends on item J. And this makes sense. If we are a number of people, we are running different campaigns, but we have all decided to bid on this current set of impressions because those impressions match our targeting criteria. So suppose it is criteria is all young, so you show young people between 18 and 24. So that's one criteria that's met by all. We all bid, right? So the first thing is the price to all of us must be the same. It cannot be different. And this is where that utility framework doesn't make sense, because the utilities says each one is going to get different utility. And what this theorem tells you is that if you all bid on the same item and you may be different, it should not depend on your campaign and only on the item. And so you get this, that Xij is Xj, so it doesn't depend on I, and that allows this reformulation only in terms of J. Okay. So you've gotten rid of the i's. And in terms of the acquisition costs, and you can write this in this quantity, and if the solution exists, then the bid is just the inverse of this at Sj, because you found the Sj for each I belonging to Bj, and the allocation is just Rij divided by Sj, because Sj is, after all, the sum of all of this, and so what you need is just a normalization to get the allocation. Right? So you have taken your original formulation and reformulated it this way. And so we need one assumption before we can solve it. And this is the problem of a question of adequate supply. Basically saying that the market is such that you can always somehow manage to cover what you require. If necessary, by bidding high, but there is always supply in the market, right? Adequate supply thing. Otherwise, this problem is not well posed at all. And in fact, what we do, this adequate supply condition is nothing but a Slater condition for this nonlinear optimization problem. But it's not a classical nonlinear optimization problem, because why? We have these integrals from 0 to t. So it's actually a classical calculus of variations problem. It's not so it's calculus variation, and so for the tools that you have to use are Pontryagin's maximum principle to solve this. Right? So you cannot use classical nonlinear optimization theory. Okay. So now, once the adequate supply assumption is done, you have a strongly dual problem. And so you can formulate a dual. And what is a dual? It tells you that if there's adequate supply, the solution of the dual is going to give you the solution of primal in terms of costs. But we'll see what the dual buys us here. So recall, there are these mu jk's, which are the dual variables, and these quantities rho I. The key is that this mu jk turns out to be something called, to be interpreted. It's like a shadow price. So it is really what we call a pseudo-bid. And this is the quantity you need to bid. But there's something very, very nice one can show. When you formulate in this case, if you look at these pseudo-bids, there are only a finite number of them, where each bid is valid on one of the intervals. So suppose tk minus 1 was a time at which a certain contract went off. And now the next contract is going to go off at tk, the next one. In the interval tk minus 1 to tk, you have to only look at all those campaigns that are active. And the mu is going to be constant on that interval. And then for the next interval, another group of players is going to be constant. So it is piecewise constant on these intervals. And what we know, because there are a finite number of campaigns, there are a finite number of these intervals. So mu is finite dimensional, as opposed to be an infinite dimensional function of time. And that's a very remarkable property of these auctions, that you really have these finite number of pseudo bids which are going to allow you to make a bid. And so the immediate question is, I've talked about this in great generality. And the question is, what is the connection between first and second price bids? And when written this way, and you write it in terms of all of these quantities, you realize that the second price bid, if you only look at the Lagrangian, which contains the problem, if you plug it in, you see really that it is the first price bid in the cost function with this removal of this ci rho I, and rest of the constraints are the same. So one of the things you immediately realize, that any bid that you're going to make, whether in the first price auction or second price auction, you have to be the highest bidder, otherwise you'll not win. So it turns out that the actual bids, whether you place it at the first price auction or a second price auction, the actual bid amount is going to be very, very close. And then I claim it is better to pretend that you're bidding in a second price auction than bidding in a first price auction. Because in a second price auction, we don't need any assumptions other than continuity for the supply curves. So you don't need to care about it, right? And so the first theorem says that, well, what are the bid values? So the bid says that, well, I can define these various functions, G and so on. Sorry, I have to always forget that. And what it says that the bid is just the pseudo bid in the second price auction, and it is the pseudo bid of the first price applied through this inverse map of this G function, which is the derivative of the cost with respect to the derivative of the supply curve. So we have to assume supply curves are C1 here. Okay. And so we got a way to exactly evaluate. So the upshot of this calculation is the optimal bid path is constant between contract deadlines, while in the first case, pseudo bids need to be mapped through this function G inverse. And what is the intuition? The intuition is that in second price space, you're protected from overpaying because you're always going to pay the second highest price, right? Whereas in a first price auction, since you're the winning and you're the highest bidder, you might tend to overbid. So you have to correct for this function GT to try to keep your bid as low as possible. And so therefore that G function is coming, which is a function of time, T. Okay. And if the supply curves are time independent, right, then G inverse also turns out time independent, and you can conjecture that these two must be the same, but actually they're not quite the same. They're very close. And therefore, the solution to the optimal bidding and allocation part consists of this XT and gamma T, right? So one way of implementing this policy is the following. Upon an arrival of item of type J, bidder should sample a random index from the set Bj, right? I, according to this distribution, which is gamma ij, because that's coming from your optimization problem. So let I hat be that sample. And then what you do is you allocate that to the campaign I hat and continue, if you want to think of it as a randomized algorithm. Okay? So this is really how this thing works. And so this is this, like I said, you have xij, which is the wj inverse of the function st, which is coming from the optimization problem. And the allocation is again coming from the solution of the optimization problem and the quantity sjt, right? So this problem is still infinite dimensional because this st and Rijt must be solved as there's an integral from 0 to t involved. So it's really an infinite dimensional problem that you need to solve. And what happens is you can show that the solution actually involves integration and slows down the algorithm. And you want the algorithm to work within 200 milliseconds. So this again comes back to engineering. You want to make an algorithm scalable. So what we found, it's easy. Oops, sorry. I guess my mom calling to find out am I doing a good job or not. Okay. So okay. So what we found, in fact, is discretize the primal problem that we originally posed in its form for lambda. Okay. And solve that problem, discretized problem. And you can show that if you take the final time and divide, say, into k steps, then the error is of the order 1 by k. And so if you choose k sufficiently large, you still get a finite dimensional optimization problem, because right, it's a discrete optimization problem, and you can make it work sufficiently fast. And this is what we realized is better. So now I want to just finish with some discussion of ideas of what Monte-Carlo simulates. So how do we simulate this problem? So we have these measured curves, right? Supply curves. So what we do is we generate these samples from these measured curves for these various J's, right? and treat them in our simulation as the items arriving of that type J. Run these algorithms because those are the amounts. And so what this function shows, or what this thing shows, is that I have the first price and second price. And what it says is I look at normalized thing. These are the contracts divided by the total number that I get. And the thing that is most interesting here is to look at the last row. You find that after running these pricing algorithms on the simulated data, you're roughly getting 90% fulfillment of your constraint. Why is this happening? It's happening because we developed a theory for averages and we're applying it on random instantaneous rates. Right? So it's not going to really be the optimal thing, but if you formulate the stochastic problem for which you do not know anything about the dynamics, it's impossible to do anything. So the question is, how do you do this fix in life? Is instead of requirement constraint of C, you increase the requirement constraint by a factor delta, and you show that you can adjust the factor delta so that you get complete fulfillment of your contracts. Perhaps you'll pay a little bit more, right? But the actual amount that you pay is very small compared to the actual contract. So there are two uses of this type of work. One, it actually tells you how to bid. And two, if I'm a DSP, I can solve this problem and look at my past data, and it gives me an estimate of how much I should charge for a contract if I want to make a certain percentage of profit. And the most interesting thing is when we did this and we gave our results to addictive mobility, right? We found that based on past data, they would have increased their profitability by 60%. So they were doing something purely random. And our belief is all players in the market are doing that. Okay? Because none of it is based on this. And believe me, this is the type of thing that it comes from the actual way these people formulate the problems. It's not based upon utility curves of users and so on and so forth. This is the actual thing. And this is what now addictive mobility is using in their implementations of how they do. Okay. So with that, I'll stop you. So for example, so the various things I can try to say is that one of the things, like I said, we found very surprising is that the bids for the first price and second price auctions are almost the same. They're very close. And that's not surprising because you want to win. You want to win while keeping your costs low. Okay. So you come up with almost the same bid. And therefore, given that the second price auction only involves computing the pseudo price, which is the dual variable of that optimization problem, rather than mapping it through that function G, just solve the dual problem. And that's a much easier way to find the bid. And that bid is going to be very close. These two bids are going to be very close. And so even if you are bidding in a first price auction, treat it as if you're bidding in a second price auction and bid according that way. And you will get basically the same bids. And of course, your costs are going to be different because we know that the first price costs are much higher than second price costs. So what you pay will be, of course, higher, and you have to take that into account as a DSP when you want to see. So with that, I'll stop. I'll just put the relevant references. So the first paper was published last year at Sigmetrics. And the second paper is under submission. And this is some other related work. So of course, there was a paper by Gumardi, Key, and Alexandre Poutier, where they only looked at IID arrivals and one type of item. So no targeting sets and no intersection of targeting sets. And of course, they use utility functions, which is not very meaningful. And they had a constraint on the budget as opposed to constraint on the impressions. This paper by Santiago Balseiro and Best and Weintraub tried to look at a mean field version of this problem, but really, again, they had one targeting group and they assumed IID arrivals for the. Of course, you see, if you have IID arrivals, that makes your estimation of W very good, because even if you have a censored observation, you can measure W of X. But that's not the issue. The issue is you have to estimate these supply curves. And that's the way you can formulate and calculate your bid. So with that, I'll stop, and I thank you all for your time. Sorry to have gone up a little over time, but I'll take any questions if you have.
Thank you, Ravi. So are there any questions in the audience?
I have very basic questions.
Okay.
I'm not that familiar with.
That's okay. I mean, there's nothing. I mean, we are all learning new things. Okay. So
what's the point of second price auction? Why do we do that?
Okay, there is a long history and theory. So the question is, what is the point of a second price auction? So there is a long theory in economics. There is a second price auction is called a victory auction. And the idea, and you can read this in many books and papers now, the thing, is that by paying the second highest price, even though you bid the highest price to win, you sort of create what is called a revelation principle. That means users will reveal what are their preferences. And you can prove this mathematically under, of course, certain idealized conditions, that by running it as a second price auction, the user preferences are revealed, right? And so I have no incentive to inflate my expectations when I bid, if I'm bidding in a second price auction. So that was the theory.
Yeah, okay.
And in some sense, if you look at all these spectrum auctions that went on, you know, like I know the spectrum auction in Britain, it was conducted based on second price auctions. And again, the reason is because of this belief. Of course, you know, this is a static setting. In a dynamic setting, you know, things change. But that is sort of the rough reason why people use second price auction.
Ravi, perhaps a question which is, so there was a lot of activity, I mean, around Peter Key and the group. Do they go on working on these questions?
No, I think after this initial paper of Gumardi and Alexander, they really didn't have any follow-up work.
I see, okay.
The follow-up work moved into the business schools, and that's why the Santiago Balseiro and all these guys, they are at Columbia Business School and Stanford, Gabriel Weintraub at Stanford. So they wrote a whole series of papers. Mm-hmm. But again, I believe they missed the essence of the formulation because they never talked to a real practitioner.
Mm-hmm. Yeah, for Peter Key, they had similar motivations. I mean, it was really for these online things when you have ad and you have some knowledge of the user, the one that you cited at the beginning, right?
Yes.
This was really their fundamental motivation. And so could you say a few words again on the main differences between, I mean, the twist of a viewpoint between their initial thing and what you did here? Besides the IID thing, right? So
first of all, what they tried to do was a one period optimization.
Yeah.
So the temporal aspect was not there at all. That you had these contract deadlines. They just tried to find a rule to get an average cost optimal, given utility functions of users. Mm-hmm. Right? And they believe that, and in their model, there was only one item at a time arriving, not many items. So one item at a time arriving, and it was arriving as an IID process. So either it was there or not there, right? And they had only one type of item. So that was a big difference. So they did not allow for mixtures of targeting sets and so on and so forth. And it was just over one period. So that was really, but the mistake I believe they made was really formulated as a classical kind of problem where you have, so what they really showed is that you have to bid a slightly inflated price, which they call a shaded price. Okay, so that was the basic structural result. And that shaded price came because the criterion that they used to optimize was the discounted cost criterion. Okay, so you have this IID, you want to minimize the expected integral 0 to infinity, alpha raised to k, some cost function c of xk, dk, right? And these xk's are chosen to optimize the utility functions where user of type 1 has a utility function. But they did, they in fact had homogeneous users in their paper. So they just assume that there's a utility function u of x. So if they bid x, they get utility x. And then they try to solve this problem. So it became a very simple Markov decision theory type problem.
Yeah.
Okay.
Okay. Thank you.
And of course, they had a budget constraint, but they didn't have an impression constraint. They had a budget. So you bid, and your total budget is less than or equal to b.
So I've got a question. Maybe should be the W function. It's not depend on your own strategy. Okay, so you adapt your strategy based on what the others do, which is the W function, but you assume that they don't do the same. So what happens if
so everybody is doing the same, and therefore the W of x is the kind of see, W of x is related to the maximum price everybody's bidding, and hopefully everybody's bidding the same way. So there's homogeneity in the approaches to the problem.
Okay.
But those curves that we got, right, which I will go back, is actually based on measurements from real data. These curves is actually, so you have two different items, and you see they have two different supply curves.
So it's unclear if in real life the competitors do try to spy you.
But you see, it really doesn't matter, right? You just try to measure what is the average supply that you get. So the only assumption you are really making here that somehow you can estimate this, right? Because if you cannot estimate it, then you cannot solve the problem. You cannot come up with any algorithm to bid.
Question about the stability. If everyone tries to do the same thing, would it naturally converge to what you want, or could that be?
You see, what Best and all these people showed is they took, again, you have a single targeting set. These items are arriving IID. Okay. And then they said, let's look at it as a mean field situation. So when I bid, I see an average of everybody else. And the average of everybody else is Wx. But it's assuming that users are all identical. Right? Otherwise, you cannot get anything. But they also did not realize it is W of x that they need. They just they solved the mean field. They said, let's assume X bar is their bid of these other guys. And so my bid needs to exceed their bid. And I'm going to pay X bar, which is the maximum, X max, which is their bids. But because the users are independent, it's just the maximum of those random variables. And so that's what they did in their paper and showed that the mean field, there's a way of looking at it as a mean field. So you can think of this W of x as the average coming from a mean field, if you would wish to look at it. But that's not how I wish to look at it. I just go and I measure. So the way really you have to do is remember that there is a notion of exploration and exploitation. So typically, for example, what addictive mobility will do, okay? They keep a certain budget aside from the total budget that they have received for the contract, okay? So the initial part, what they do is they go to these exchanges knowing on what type of things they have to bid. and they will bid high to win every time to know the price. From that, they get the estimate of W of X. And then they use that estimate of WX going forward for their bids. That's how you do it in reality. There's no other way to do it. Because nobody, so these WX is private information to these companies. Nobody publishes them. But that's what all companies do. They spend a small part of the budget to explore, they estimate, and then they move. It's not perfect. But what we showed is that we went back to the original data, and the original data was more than 30 terabits of data they had. That's correct. And applied these algorithms. And we showed that they would have had a profit of 60% more every year. If they're used, because what they would do is, okay, I saw that the average bid there was like, let's say, 0.0015 cents. So they would put a bid, and typically exchanges have floor prices, right? They have floor prices saying that we will not accept a bid any less than 0.0001 dollars. So they have these floor prices, and then so the guy will go and say, I'm going to put a bid between 0.0001 and to a maximum of 0.0025. And they put this bid out in this. That's what they were doing. And everybody must be choosing such things. And then they actually look at who has got the highest of these numbers, top bids, and allocate it to that. And use the second highest thing. So that's how exchanges would do it, because they have no other basis. But when a theory like this comes around, it tells you exactly how much to bid. It doesn't give you these things. Right? So this was, I think, our great, our contribution to this problem. That we showed them how to formulate it, and we showed them how to bid. Now there are other aspects of the problem which is very different, right? Which is how do you measure W? I know measuring W is okay in a second price auction. In a first price auction, I don't know. Right? I only know I bid X, I got W of X. Thank you.
Other questions?
Hi, sir. Do you hear me?
Yes.
Yeah, I had a question also on W. So you estimated on past data using what you said earlier. In your presentation, as also W was parameterized by T. So it was also.
So you have to measure at different periods of the day.
I mean, it's on past data. How do you make it dynamic? I mean, what I understood.
No, we don't make it dynamic. So the reality of how it's done in practice. I don't know whether you see this curve.
Okay. Yeah.
Top curve. Yeah, if you look at the top curve, you see these looks at the rates that come at different hours.
Okay. Okay.
Right. So you will take a slice like this and estimate in that slice for every day. Okay.
Okay, I got it. Great, thank you.
Because we have no model. We don't have a model on how this evolves. But we believe it's periodic. Okay. So it's just, I mean, in reality, that's all you can do. You don't have models for these things. So, I mean, the way I look at it is by doing all of this, we were able to give addictive mobility a way to bid, which is based upon something rather than just arbitrarily bidding, which they were doing previously. And according to addictive mobility, almost all the bidding companies were doing the same things as them.